All right. So so now we're on record. What we will say? Oh yeah, rapid prototyping first. So we have when is it? Monday.
So yeah. How many of you are signed up for rapid prototyping? Starting off this, okay? That's promising. Good. How many of you have it in your schedule? Do you see it there? The schedule times?
In your calendar.
Cool. How many of you finished rapid prototyping? Okay, so you kind of all need to go through that, right? Is that correct, Marge? Everyone needs to go through it. So we run rapid prototyping as a course, which is a bit unconventional. So it's not surprising that some of you are signed up and some are not. It's technically a second year / third year course. And the idea is basically that you have perform three game jams, if you like, right? So in different fashion, individually, in groups, all the like. So in order to get a passing mark, right, you need to write a report and reflect on it. So basically it means you do precisely what Marish just said before. For the fun of it, you're developing, over 2 days, you're developing a game or an application or whatever it is, right? Something related with programming, of course. So everyone needs to pass that course as part of your curriculum, the degree. And you have basically until your end of your bachelor's to do so, right? So 3 jams, 3 weekends. So the idea is there to encourage you as early as possible to actually participate in that course and get done with those jams. The earlier the better, rather than dragging it into when you're officially signed up, which may be next year for some of you because of, I don't know, whatever reasons. So
yes, question.
Yes, please.
When is the first one and where can I write myself up?
Yes, exactly. So the first one was this weekend, but that's not a problem. So just to scare you off a bit, but we generally have set, or we don't generally, but next week we'll have a session on Monday at, remind me, 12 o'clock.
I think it's Monday 10 to 12. Yeah.
Let's do the verification thing.
Yeah. I don't have my phone with the calendar, so.
Yeah, it's
12. 12.
So 12
sorry.
in the Cisco lab. You guys know where the Cisco lab is, from 12 to 2. And so we're not necessarily meeting there always, but always before jams and after jams. Sorry? Yeah.
It's called Cisco Lab, so it's downstairs in that corner. Oh, actually, in that corner. Yeah. Yeah, in that corner. Yes.
Here. I think you can find it in Maze Map as Cisco Lab, even described.
Yeah, it is called Cisco Lab.
So it says the room number in parentheses Cisco Lab. So you will figure it out quite quickly, I think. Or you do a control. You actually go to rapid prototyping on the NTNU webpage, and I think you can click on the room number or something like that. Yeah. So the key thing is, perhaps if you haven't taken the course yet, please join us next Monday, because we actually do a post-mortem basically presentation. There's one student left from the last weekend's jam who hasn't presented yet, so we'll see how the presentation format is. And then we can again go through the mechanics of the course. But we encourage you, if you want and you can handle it on top of your current course obligations, to show up and start thinking about participating.
It's A058.
There you go. A058 is the room number for the Cisco Lab.
But in the course schedule, it is called Cisco Lab.
Cool. You can click on it, right?
Yeah.
Cool. So
and
you can
get to Maze Map. Yeah.
Cool. That was pretty much everything we want to say about this course, but keep it in mind, right? So when it runs effectively both semesters, doesn't necessarily show up in everyone's schedules at any time, but it's kind of an odd course because it's stretched over the remainder of your studies, basically, right? So, but everyone has to do it, so the earlier the better. Next Monday is a good opportunity. If you can't, of course, well, then you need to do it later, but just bear in mind, you will not, finish your degree until you pass that course, right?
Yeah, so that used to be the case.
Okay, now we go.
They are second year. I don't know when the change was. Do you still have to pick the track, or it's flexible to you? Yeah, you have to pick the track. Then you have to do it if you pick the gaming track. If you pick the app track, you don't have to do it. Yeah, it's automatically extended, so you can take it next year if you haven't finished all the jams.
So you could, for example, do 1 jam this year, and then next semester do a second one, and the next following semester a third one. You can stretch it out arbitrarily long, so it's not a
until the 5th semester.
Yeah, so until you want to graduate, yes. Yeah. So that's sensible. But it's not like you need to finish it by summer.
So the rapid is only for the game track?
No, it's for both. The rapid prototyping is open for both, but Yeah, I'm not sure. Like it used to be required course for the game programming bachelor. Once we split the tracks, I will have to double check in the documentation if it is required or not for both, or just for the game track. But both can do it, and we have students doing both. Like we have students doing the app track.
We have always app students in there as well, so it's open to yeah.
You can do some graphics demo, you can do some application, mobile application, game, whatever. It doesn't matter. It's called Game Jam, but it's sort of just jam. Yeah.
It's usually topic centered or feature centered.
Yeah.
You're on the game track. You have to do like game jams, or can you like make an app?
You can make apps as well. Yeah.
There's no constraints. It's just working around the topic that we give you, and you need to do something related to that topic and something that has to do with computers ideally as well. So in order to pass it, and then in the end you reflect on it by writing a mini report in the group setting you have been working in, or individually if it was an individual jam.
Yeah.
Join us next Monday. We'll talk about the mechanics in more detail, and then you can ask more questions there. But just because I hadn't seen any one of you showing up there on last Monday, so but start thinking about it.
I didn't know it was there at all.
Exactly. So we're not blaming you. It's just announcement. Please come.
Yeah, exactly. So I don't know why it didn't show up in the curriculum for some of you, maybe. But we have the students who are showing up, which were signed up last semester for it.
That's right. So many of those finishing up, well, they know the rules, so they know they need to wrap it up anyway. So
yeah, exactly. Is it possible for one of the tables at least have the slides? So I see, where are you? Okay, so, yes?
About the quick prototyping, I'm trying to sign up for it right now. You can only sign up for the assessment, but not the lecture.
Yes, there's no lectures per se.
That's correct. So there is no real classes. It's those sessions, those gems, and the assessment you're signing up to have the course points allocated to your degree, right? So
it's by no means every Monday that we meet there.
No.
We only meet there in preparation for a jam
exactly.
or afterwards, right?
Exactly.
So that's why next week is a good opportunity because we will meet. The week after that, probably not. Right?
Exactly.
So if you want to get more information, that's the time to come. That's why we advertise.
So, and we advertise when we have the session on Discord.
And a GitLab, right?
And and GitLab as well.
So you were asked to join GitLab as well, so you see actually what's on offer if you like, and then participate.
And
heads up, 25th, I believe, we have the Global Game Jam, right?
In Hamar. Yeah.
And we are.
And we will run the local copy. Yeah.
So next opportunity in 10 days would be roughly.
You don't have to participate in all the gems, so you only need to participate in 3, right? So we run probably about 12, like at least once a month. So there are 12 in a year, so 6 in a semester, roughly speaking. And then 3 of those you have to participate, you pick, right? During the summer we don't run, yeah. So we run more frequently than once a month, but it kind of adds up.
External events, right? So
and we have external events, yeah.
So in some cases we count external events against the jams, right? So not necessarily that you need to do them here or can do them here, but you can actually participate in other external activities and get them
counted towards the course.
That's right.
You mean like the Hamar Game Jam?
Exactly. That's a perfect example. Yeah. So if you're participating in the Hamar Game Jam, you tell us what you've done, and we count it as one of the gems.
Or Hack for NO, or any of those. So
Hack for NO, or
So
we have a list of different external
local and external. So, but if you don't want to travel or want to deal with this, sure, we have enough locals on offers as well. But it's I think quite attractive to actually do at least one external one as well to get a feel, with the bigger different community. So you can actually connect as well, which is as much the purpose of those jams as it is to get something done.
Right. Okay. So any questions about the practical exercises? So what I've done, like if you go to the wiki and you have the basic Java, it's like a very simple exercises for a very fundamental things in Java. So reverse a string, make a lowercase character, and then there is a fizzbuzz. Fizzbuzz is kind of simple, but if you try to do the additional tasks, it gets quite complex and quite involved. So you can think how would you do that if you were to make it kind of robust, right? And then it's not trivial actually. Reading a file, counting words from a file, and specifying multiple words to be counted. Like how would you do that? Like counting a single word is quite easy. You can take one parameter, you load the string, and then you count this one string, one kind of a word across your string, right? You can do it in a loop, or you can use some regular expression to do that for you, right? But if you have multiple strings, how would you organize your code? How would you do that? How would you make it flexible that you can specify one or multiple keywords to search through a file? So think about it. As I'm saying, you don't have to code it, but I encourage you to code it as a practice. But just explore how would you do that. Then we have the more advanced ones. So we have a couple of concepts. The first one is JSON. It's there, but we will talk about JSON later. So we have kind of a block session allocated to talking about JSON and object serialization and how you do JSON calls from Android. How many of you worked with JSON before? Yeah, some of you worked. Most of you didn't. So how many of you know what JSON is? Yeah. So we kind of have a bit of an introduction, but you can have a bit of a head start if you try to think how JSON parsers work in Java and how to use them. The second one is an object-oriented pattern for a switch statement. That one is, how many of you know how to do this? How to make a switch statement without a switch statement? Using an object-oriented pattern. Yeah?
Are you thinking about like the instance of an object, or are you thinking about
Yeah, you could use instance of, but if you say if instance of, then you have to have if statements, right? So the task is you have some hierarchy. Yeah, to use polymorphism. Yeah, exactly. So how would you do that? Like you have a hierarchy, polymorphic hierarchy of some sort, and then you have a base type, and then you have a container which has items of that type. Like let's say a list. That's what the task says. So you have a list of items, and then you need to do something on each of the items, right? So normally in the normal structured programming, you would say if item is an instance of this, do this, right? If it's instance of that, do this. Or you could have a case statement. But in object-oriented fashion, you would normally have, like, that's what you do with GUI elements, with, like, you have a draw method, and then if you have to draw some item on the screen, you don't care what it is, you just say, pick me an item from the list and call a draw method. And it will do whatever it's suitable for that type, right? So that's normally how you use polymorphic calls, that you say a particular instance of my item will do something specific for that type, right? But in this task, the behavior is not part of the instance, it's given from outside, right? So I'm specifying the behavior is external to the type, right? Yeah, interface?
Like says you have to have these certain methods and then implement the interface.
Yeah, so how the methods and how the interface would look like.
And the interface would just have the header for the method, so it wouldn't actually have the implementation method.
Yeah.
If you implement it, then each class would have to give their own implementation of the method that they implemented. So,
almost.
Yeah, almost. Yeah.
So the way it works in kind of the object-oriented pattern is that you specify, as you say, some sort of interface which the behavior implements. And the interface has a very specific kind of look, because it only has one method which accepts different types of that method, right? So with the polymorphic thing, what we do is we take the item and we say item.draw, right? And the behavior is attached, is part of the instance. Here, we are passing the instance into this implementation of the behavior, which has, let's say, execute method. And the execute method has multiple instances of execute. One takes an item, which is the abstract one, and it says, I don't know what to do for the item, for the abstract type. And one will have like square or whatever your instances are, right? And then when you call it with the particular instance, it will do pattern matching of the types of what you're calling it with. and it will execute the correct behavior. So you'll have the implementation having, say, execute method for this type, execute method for this type, execute method for this type, and so on. And that's your kind of case statement, right? And then you pass it where whoever needs to execute those different behaviors on different types, and you do it, right? So if you've never done it before, I kind of invite you to implement this for this particular use case. Very trivial, but to get the feel, right? Where do we use it? Well, we use it every time we have more than 2 types, which we have to check for. Like if you're dealing with 2 types, you can say, if you this type, do this, else do this, right? We can do if else, it's fine. But if you have 10 types, then it gets kind of cumbersome, and then you use this kind of pluggable pattern to deal with it. And we often use it for processing language, for doing abstract syntax trees, or for traversing some more complex data structures. So that's the object-oriented case statement. We know that anonymous inner classes and lambdas are a little bit conceptually hard, right? So there are 2 very trivial tasks to do, and if you know how to do them, you're fine. But if you read them and you don't know how to do them, then try to do them and then come back maybe on Thursday or ask me like, okay, how does it work? Why does it work this way, right? So we may spend a little bit of time explaining how anonymous inner classes work and how lambdas work. They might be a little bit problematic. If you come from Python, you probably have used it before, either knowingly or unknowingly. If you come from C++, you most likely haven't never thought about it, right? Unless you're using a modern C++ with lambdas for some algorithms and things like that. Those concepts are a little bit hard, so check it out. If you know how to do it, then that's fine. If you cannot do it, then post an issue in the issue tracker or ask during the class, and we spend some time explaining it, right? Yep.
Does it work? Is there a way of specific?
The lambdas? Yeah. Lambdas, yes. They small, of course, syntax is different, right? So syntax is really different between Java and lambdas and C++ lambdas. And also, what is a little bit different is that in C++, the lambdas get kind of turned into functions which are inlined, or conceptually you can think of them as functions. In Java, they always turned into objects of the particular type because you don't have just functions, right? So there is always a wrapper which encapsulates the behavior, which is a type of, which is a class, not just instance. So that is a little bit different, but the rest is the same. So the lambdas in many programming languages have the same sort of underlying conceptualization. All right, and then I also specified the final one, which is for sensors. That's a few weeks from now. You don't have to worry about it for now, but after we have lecture about sensors, then those exercises are useful, and some of those are quite complex, right? So some of them require you to do multiple things. So probably if they are not part of the lab, then yeah, you just check how to do them. You don't actually have to do them. All right, so now if we go to the first slide deck, which is the background to mobile technologies, and it is a little bit about the background for the course, like why do we have the course and how how does it fit into the kind of a bigger scheme of things. So historically, you know, mobile computing didn't came up as a thing out of nowhere. It kind of came out of the telephony and telecommunication, right? So the you know, Graham Bell invented the telephone, like, so we can transfer kind of a voice data over the wired connection, and then we turned this out of convenience and flexibility into a wireless setup. And as the wireless networks for voice communication were growing and becoming more and more complicated, we evolved to a point where we started using the data channels to pass data between the workstations. And then we had this explosion of portable devices which got more and more powerful. That is relatively recent. So when we started developing the mobile course back in 2008, I think, or 7, the devices which were available on the market were much weaker than what we have today. There was like a very huge exponential growth in terms of GPU and CPU capabilities for the mobile devices. So the first slide, like at the beginning, talks about this audio communication. You can, check it out, how the telephony works. We sort of expect you to know a little bit about voice communication. How is it possible that you can pick up a handset in your house, dial a number, and somebody else's phone rings in the other part of the world, and they pick up the headset, and you have kind of a direct connection, right? You don't have a direct line connection anymore. Almost all telecommunication operators are not using kind of wired backbone networks anymore. They use switched networks. But that is kind of an amazing feat of engineering, how this happened, that we had this kind of implemented as humanity, globally. So let me just check. Yeah, I'm not talking about this during the slide. So just a very quick recall. What is the connection-oriented network? So in the original telephony network, what happened was your phone was wired to kind of a switchboard on the street, and then from that you were routed to, let's say you have 2 houses, right? And you want to talk to somebody in another house. So you have to have a cable going from your house to another house, right? But it's just peer-to-peer, just one-to-one, right? It's very inflexible. So what if you have a street of houses and people can call each other like from one house to another? What you have to do? You have to have a switchboard where your cable goes into a switchboard and everybody's cables go to the switchboard, and then it has like sockets, right? And then if you plug kind of a little thing which connects one socket with another socket, then you close the loop, right? You close the connection. And then 2 people can talk with each other. Make sense? Okay, so initially there was a human who was in this box, and you pick your phone and you say, I want to call Tom. And she says, oh, Tom is here. Okay, wait a minute. And then she this like plug you with Tom. And then Tom phone would ring and you say, oh, hi, Tom, and you talked, right? And when you finish, she would unplug you, right? So after that, the invention happened, and we realized how we can do this without a human. We had a kind of AI. It was like a mechanical thing where you dial it in and it would know which one to connect you with, and it would kind of connect you with the particular slot, right? But as you can imagine, this switchboard has a particular capacity. It can only work with the kind of connections that it has, right? So how do you dial another city? Well, you have to have like a local one and then more global one somewhere else, which connects across cities, right? So we kind of invented this hierarchy. So from your little street, you can call into town. From the town, you can call to a country. And then from the country, you can call an exchange in another country. And that's why we have country codes for dialing in, because if you dial in, it's like a routing of where your signal should go to kind of connect you and open the connection footer, right? So your telephone number is like a basic route of what the signal needs to traverse to reach your final destination, right? So it first is like a country, city, within the sub-city area, and then a street. And then within the street, it's the final bit of the switch, right? So you kind of navigate the pathway. And in the early days, it was all physical. It was all based on the actual wires being connected. So that's what made it possible for modems and for direct communication, because you basically had a physical cable connecting you to somebody else, right? All this infrastructure was actually wiring you up, right? But what is the problem with this? So if you were to design it for Norway, what would you need to do? Yep. Yeah, maintenance, but maintenance of what? The wires, exactly. So you need those boxes, you need those switchboards on your street, in your city, right? And in between cities. And between them, you have to put cables in the ground which connect them, right? And how that cable looks like? You can Google it. It looks like a huge, thick cable which has thousands of little cables inside, right? And you have to dig it in the ground and maintain it, right? And then if there is a suburb, there is a new, boost in housing somewhere, and there is a new population coming in on the suburbs of Jovik. We have another 5,000 people moving in, right? How are you gonna deal with it? Well, you need to dig another thick cable to connect them to the rest of Norway, right? So this is kind of like connection-oriented networking, where you do the switching based on the circuits, right? So it's called circuit switching, right? You have actual physical circuit between the source and destination. So what invention do we use these days to browse YouTube? Do we have a circuit connecting us to the YouTube channel or YouTube server? How does it work? How can we see YouTube video from the server? So let's say we have 60 people in the room, and let's say I have a streaming server here, right? Let's say we have a streaming server in US, and now all of you open a website and start streaming a video, right? Do we have to have 60 connections, 60 little cables going to US to be able to view it? How many cables do we need? One, exactly. How is that possible? That we only need one cable to US? Yeah.
Because our access point is wireless.
Yes, but what else makes it possible? Yeah.
It's the cable can have lots of different signals simultaneously because it's rather than the small anyway, you can send the light to different frequencies that you tell each other.
Perfect. So on the lowest level of networking stack, we have physical layer, which allows us to do multiple things on the same medium, right? We could use a copper wire, or we could use a fiber optic to do multiple things. How is this called? That we can do multiple things over a single medium. So the one thing is called circuit, which means we are assembling kind of a connection between two things, and then once the connection is assembled, they can do whatever they want, right? The connection is theirs. It's like 100% dedicated to them, right? That's how the telephone used to work. If we were to share a single copper cable, we have to divide it into chunks. And then if we divide it into chunks, we do some frequency modulation, for example, so we can pass multiple things through the same medium, right? That's how some of the analog telephony works, and that's how broadband works. Broadband works because you can squeeze multiple subscribers over a single copper cable because they use different frequencies, right? But then we have another mechanism. This mechanism is for streaming. When you're watching YouTube or when you're talking on Skype, do you have continuous communication? Like, is the connection open and you have kind of continuous signal traveling, like audio waves? Or do you have packets traveling, right? We have packets traveling. So we don't have, like in the old days when you called somebody, you have actual voice wave traveling over the cable to the recipient. And the voice quality was great, right? But nowadays, what we do is we digitize the voice, cut it into small packets, put the packets on the network, and the packets can travel. And one packet is traveling, other packets can travel as well, right? So you can have multiple subscribers going over the same medium because we're doing packet switching instead of circuit switching, right? So there is the concept of circuit or packet switching, and the packet switching is much better because you can squeeze out of the medium as much capacity as possible, right? In the old days, if you have a single copper cable and you have two people talking, right? there are breaks. I'm not saying anything. So there is nothing traveling on the wire. I'm wasting the bandwidth already, right? Somebody else could be using my empty spaces to use it for data communication, right? If we using packets, we can pack and use 100% of the capacity that we have on the wire for multiple subscribers. And then using fiber optics, we can squeeze more and more because they are fast. So modern telecommunication companies, when they dig cables, they don't put those thick cables with a lot of wires. They put, I mean, they kind of do that, but the wires are fiber optics wires, right? So they put a wire which can be used by thousands of subscribers at the same time, and that is providing them enough capacity to grow and expand the end customer base without the need to dig another cable, right? They want to dig the cable once and have it sorted for the next 20 years. Even if the speeds and even if everything grows up, the kind of the core network capacity is sufficiently large to deal with the volumes. So we have, like, you know, again, we kind of finishing the first slide. It says processing power, and we have analog encodings. So that's what we used, and that's what you mentioned about this modulation, frequency modulations, for example, or amplitude modulation technologies for squeezing more subscribers on a single line. And then we have digital encoding. So if we do digital encoding and we encode voice, do we have to encode the full spectrum of voice, or do we need to only encode the frequencies which humans hear, right? We don't have to do the whole spectrum. We just do from, I don't know, from 20 hertz or 40 hertz to 16,000. The rest we filter out, which reduces the data that we need to encode. But what it means is that with the modern telecommunication companies, we cannot use modems anymore because they cheat in a sense that there is no wire connecting you with your neighbor. It's all encoded digitally, right? So in the old days, I could actually call my neighbor, and instead of talking with him or her, I could plug in my analog modem and communicate digitally over the telephone line. In modern times, it's almost gone because all the voice is just for voice, and you have your signal kind of encoded. So your trick with the modem wouldn't work, right? All right. Yeah, 1 hour gone and we went through the first slide. Not a good start.
That's life.
That's life, right? So let me talk a little bit about the thin and thick clients, and then we'll have a break. So what's the difference between thick and thin client for computing? You probably heard the term. Who've heard the term thick or thin client? So what's the difference? Yeah, yeah.
Thin is that like most of the stuff on the computer is done in the back end rather than on the client.
Yeah.
Thick is that most of the stuff done on the client itself.
Yep. Any other additions to that? So the simple definition is most computing happens either on the device or somewhere else. That is pretty much what it is. Why would you use thin client versus thick clients? Where have you experienced a thick client or thin client model? Yeah. Games are usually thick client modes where the server does the bulk of things and the clients just are devices for visualization. Yeah, it could be like this. Yeah.
Cell phones are thin clients, at least previously when the cell phones were rather weak. So that might have changed a bit now when the companies actually have a bit of.
That's right. So it is with the modern mobile devices, it's a little bit in between. So sometimes our phones are used as a thin client, sometimes they are used as a thick client. Give me an example. When your phone is a thick client or when your phone is a thin client? Yeah.
Well, thick clients on video games because an app you can download.
Yeah.
While most websites that have a cell phone will be light clients.
Perfect. So when you're using Facebook or when you're using Gmail, it's a thin client. The phone can be almost as dumb as it gets, and the functionality will still work, right? With games, not really. You need some processing power, and like you probably have to download quite a lot, so you have to have all your assets and like storage-wise, processing power-wise locally to be able to play a game, even if it's a multiplayer game with others, right? So it kind of depends of where the processing happens, as the slide depicts, that in the thin clients model, application runs somewhere else, like on some central shared resource, and then the client is just kind of like a terminal. So again, you can put yourself in the perspective, and you can see that the early computers were really big. They were occupying a massive amount of space, and they were shared among multiple people, right? So if this university was running 30 years ago, what would probably happen, all those monitors would be thin terminals, and in the basement we would have like a massive server room, which would probably contain just a single computer, which all of us would use, because first of all, we wouldn't afford the big computer to buy, and second of all, it was powerful enough that, you know, thousands of people could use it, right? Then we had the PC revolution. What PC changed, it said, well, you know, most people don't need such a powerful computer which is like capable of weather prediction. You can do simple computing stuff on a limited PC, right? And it democratized access to computers. Computers became cheaper, and then everybody had a keyboard and a monitor and the processing and the storage with them. And then you didn't need to have the central single computer which does a lot of things, right? And then came the cloud, and we said, yeah, but it's limited. Like, we cannot do those big things. Like, we cannot do those massive data processing searches and things. We need those big computers. In fact, the big modern supercomputers are collections of smaller computers put together into a single giant computer, right? And then the capability of processing and storing are by far exceeding your laptop or your PC, and then you can do bigger tasks, right? And then you would access a thin client. You would use the thin client model to access those resources, but it's not. So yeah, we have situations. For example, in the previous university, we had this discussion about computer labs. In some universities, they still have a concept of a lab, where there are like monitors, keyboards, and PCs where students come, work, and leave, right? And there was a question whether you should have each station, each desk having its own computer, or is it enough to have a single computer which can handle, say, 30 students working at the same time, right? And then the single computer is a bit more powerful, but the workstations are just thin clients. They all talk to the kind of a central computer which is in the classroom and powers 30 seats, right? And it's often the case. You often have that. You may go to a lab where you have a keyboard and a monitor, but there is no actual computer. The computer is like a shared resource between the lab. All right, so let's have a break. And we will talk a little bit about this thin and thick in terms of mobile phones. So 10 minutes break. Yeah, I don't think I will reach the Android file. Too many stories.
Was ein Slide wurde vergessen. Ja, old man phenomenon. Let's talk about stories. Actually, I was when I was studying with my brother, I was actually I didn't appreciate it at the time, of course. I was actually still removing terminals. So one of my first jobs was to go to all offices because they had like double sub, like some, integrate application system integration, information system integration problem at the time, right? You have one dedicated system, works with Unix, works very perfectly, inventory, but then all the communication with clients and accounting works separately, right? So they had like a desktop and a terminal next to each other, and depending on what you do, totally non-integrated or batch integrated over time systems. So my task was to remove all those terminals and eventually switch over to a client-based solution to access to that machine. So it was plugged into the TCP/IP into the LAN, and then I just need to install a terminal application as a transition phase. So at least can copy and paste between extra desktop Windows stuff.
When you transition.
Exactly. That was the way, right? And then of course eventually that AS400, I think it was, IBM, the classical middle, SME kind of setup, right? So, and then they actually got rid of the shit thing and had I'm not sure it's shit because they afterwards got SAP. So it was even, bigger and shittier. And then the whole thing, of course, got a bit more homogenized, but different times. So it was so funny. You had to program, we have a bug in this program, okay. And then they had based on the keyboard code, you would get in programming mode. When you would change the fucking code in real time, there was no versioning, no back. So there was debugging. Okay, back. Here's the application done. I mean, if by any chance any user would have gotten that key combination, right, they could have just changed the fucking program. There was no security against that at all. It was scary at that time. So I forgot the language they used. It was like a business kind of information system language. It was not one of the mainstream ones. I simply forgot. I think it's Siemens language, something like that. And funny. But shit reliable, I mean, this stuff really worked. Responsiveness was really good, and it did its job, right? So there was no left and right, so it was really algorithmic thinking. So if you need to do something, follow those steps, and it will be iron hard, it will work. Exactly, not the stupid Windows shit where sometimes it possibly works or not, right? Pretty GUI times.
There was a period when we had the TCP/IP stack easy, but it was only used between the mainframes, and in the labs for LAN, we had a separate thing, and it wasn't compliant with the TCP/IP. It used the proprietary packet format. So you load those drivers, like I remember in DOS, you were saying, okay, which ones to use, which drivers to load, and then we could have a LAN, but it wasn't allowed.
It was closed, basically.
It was closed. And then you have the actual gateway, which was allowing you to go onto the internet with the public IP address, but internally you only were using MAC addresses. The routing was actually sometimes down.
So what else was not IPX either, right?
No, IPX,
Netware.
Netware,
Yeah, that's a shit. That's a shit.
That was a problem.
Oh, yeah, it was. They had actually, but it was basically a parallel to TCP. It was
net/IPX, net something/IPX.
Yeah, exactly. SPX IPX.
Yeah, SPX IPX.
So that's the one session base. That's the same properties. Same properties as TCP.
Parallel
totally.
hierarchy.
Right? It's also layer 3, right? So it's the same layer 4. So it's the same thing, but the problem is they're inherently incompatible. That was so shitty. So we actually had them run on the same network. I mean, I assume that happened as well. You know what happened? I mean, it's like it broadcasted so much shit on the network, so it was constantly blinking on the. You were saying, what fucking traffic is going on there? And this was just print servers that used IPX, and they were just sending on
all the time.
So we had also this duplicate run. So we had print servers all on IPX SPX, and then the Windows machine and TCP already, or I think NetBIOS.
NetBIOS, yes.
And then need to have them talk with yes, you're right, the driver, the IPX driver for print servers, and for anything else,
you use the other one.
NetBIOS for the Windows servers, so you can do the file sharing bullshit, and then the really advanced one got IP addresses. And they could go on the internet.
That was later.
So that was such shit. I was admin there, right? So I was so happy when we finally got down to TCP. Everything uniform.
Standardized.
Oh, it felt so finally, world's better place kind of thing. Such a fucking thing. I mean, even hypothetically, if you would have monitor the network, right? It's so complicated to install an IDS system there because it's just too much gossip going on in so many directions. Yeah, that was an interesting time. The reason was that Novel Network established itself on the server side, right? So even the Windows clients needed to support IPS because there was no Windows server that was available and cheap, right? Because when 3.5 came out, no one did this thing. It was super expensive. But Novel Network, you could run it on anything. It was kind of the Linux of nearly. So like in terms of requirements, and NT was super expensive. I mean, you needed decent hardware at that time anyway. And I think no one really before NT4 used it seriously anyway. And you know the whole baggage that comes with the Microsoft setup anyway. So that was cheap because it also was compatible to Windows for Workstation 3.11, right? So you could use that stuff. And then I think they support.
You're right. So it was basically a monopoly of Novell who were dictating the rules because they couldn't. But the TCP/IP stack was kind of growing, and at some point, NT came along, and Unix came along, and then Novell basically killed it.
That didn't have a chance. But also they made a mistake. They never had clients operating systems. They only had server operating systems.
That's right.
So they could have had a uniform ecosystem.
Exactly.
But they
if they entered the market at that time, they would rule like Microsoft.
Especially against Windows. Come on, how complex can it be? It was so shitty at that time.
Because you could easily compete with Windows at that time, and now you switch. Even if they clone like LSD Linux, they could.
Exactly. I mean, yeah, sure. I mean, that's
how long we have left? We will go till 4.
No. I mean,
how long is the break? Another 3 minutes.
Interesting times. But that was actually cool because I remember in my university I was masters in the networking course, and they was talking about there's no other protocols on layer 3 anymore. Anyway, hang on. That was an interesting discussion. Oh, an old time. Because that was a nice example that you wouldn't get because you have this really diversity in the application area and the bottoms, but there, because of convergence already at that time. But that was a different. So you ran it in Poland?
We ran it in the labs.
Hang on, in New Zealand.
In New Zealand
as well. Yes. On top of it. What did they use it for? They used it for NDS for the Active Directory replacement. They didn't, they had pre-Active Directory. There was NDS, and that was actually. I mean, I talked to some admins. They have found it better because they already had group policies way before Microsoft even thought about it.
Right.
So, and that's why they need to be compatible. So it talked in TCP, but it needed to link to the directory service, right? That's what I mentioned. And then Active Directory came, and they just by monopoly they took over. Binary or something like that. NDS was a very good but it's gone now, right?
Novel is dead. Like Novel was dying when we had the course. We were almost deciding to teach Novel because there was discussion whether we should teach Cisco, whether we should teach Novel, whether we should teach like kind of open router, like I forgot like how it was called, right?
Right.
Yeah.
Okay.
And then
WRC.
Yeah,
exactly.
That's right. Yeah, so then we said, okay, through that we will teach
WRT, sorry. Oh, cool. Oh, so you use it in Tele?
Yeah, we use it in telecourses because we actually have a tele degree.
Yes, that's right. Alongside software engineering and information science.
Exactly.
That's right, the hard one. It's impressive staging.
Oh, it does. It's amazing, like how many things show up and then disappear, show up and disappear. Like constant flux. There is no gradual I mean, there is gradual progression, but there is a lot of that.
Yes. Baggage. I mean, so much baggage into the deal. I mean, it's actually much more noticeable in industrial context than in academia. Right? In academia, of course, the library people don't switch their stuff, but in an industrial setting, we've been training for years. I mean, we were running Windows 2000 and onwards. We still had a Windows 95 system sitting there because it was the only one compatible with the banking software. You know, those kind of legacy nightmares. Okay,
anyhow.
Old people talk.
Okay, so all right, so coming back to the mobile history a little bit. We had the phones being used for voice communication. Then we used them for some of the data transfers. I mean, let's say networks allowed us to pass data, right? So when that happened, the phones which we used to have were kind of those dumb phones that you have these days, which we call dumb phones. So reading stuff on it was quite hard, and also writing stuff was quite hard, but they could do stuff because we had like the networks allowing us to pass data, and it wasn't that slow neither, right? So what you could do is you could use a very limited phone capabilities as a thin client to do something with the more richer kind of a server sites. So if you go to a slide called Thin Mobiles, we had the ability to pass data over the data networks and over Wi-Fi, and we were able to use a thin client model to do kind of the browser as a window, and then the rest was using, you know, Ajax or some kind of technologies which allow you interactivity, right? So when we had the kind of race, like it's not really a race, but there were multiple activities happening at the same time to bring us like the first touch phone, right? And different people that kind of approach it differently. So when Apple was working on the first iPhone, they thought the mobile device will be always a thin client. It will always sort of run the browser, and then all the apps and all the functionality will be kind of delivered through some sort of a client-server model. So they designed the phone in such a way that the browser was the central point, and then they haven't thought about the App Store at that time, because they thought everything will be delivered through the browser, and the technology, the like development technology, was not existent because they thought everybody will be developing using HTML and web technologies, right? So that's how the model was. On the other front, there was development for the kind of Open Handset Alliance and some other manufacturers and some open hardware and open source projects which were heavily influenced by Linux, and they were being programmed in C++ or some other kind of languages on a proprietary operating systems or variants of Linux, and they were kind of native, so they were always having kind of a native capabilities, and they were attracting kind of developers and geeks to kind of play with them. So you had this kind of a commercial activities happening here, and those more exploratory and kind of developer-centric activities happening there. And at some point, so you fast forward 2 slides, there is a question: was an iPhone a first smartphone, and was it released earlier than Android, right? Yeah, it's a bit of a trivia. You can kind of Google it. So of course, and yeah, iPhone was released a bit earlier, a year earlier than the first Android, but there were some other phones which were released around the same time. So if you fast forward to the at the beginning slide, which depicts the Neo 1973 phone, you see a first Linux-based touchscreen smartphone, which was released kind of around the same time the first iPhone was released, right? Just a month after. So you can see that those activities were kind of happening at the same time. And what's interesting about this one is we actually had the Neo in the lab. We had the course like yours, where students were working with the Neo as a platform for developing apps and building applications. I can tell you it was a nightmare. The development was so hard that we had a hello world at the end of the semester done, right? For the good students. The phone itself was quite nice, like physically. The touchscreen was not too bad for the time being. It wasn't as responsive and so on. It was pressure-based. But what was interesting is if your phone ran out of battery, you couldn't charge it, because to charge it, you have to enable a driver, and to enable a driver, you need the power to charge the phone, right? So if you run your phone dry to actually run out of battery, then you cannot charge it. Then what you have to do, you have to take your old battery, put a battery which has the charge, boot your phone, you know, kickstart the drivers and everything, plug the power cable, then you can remove the battery and put the old battery to charge it, right? So when we were buying the phone, we knew that it has this feature, so we bought two phones, you know, so we can always have one charge and one to play with, so we never run out in a situation where we discharge both batteries. The other interesting thing was that it was completely open source and open hardware. So all the specifications for the phone were open. So what do you think it means? Yeah. Yeah, that's one thing. Yes. What else does it mean? Say it again. Yeah, it was kind of a it was itself an open source, open hardware initiative, right? It wasn't really successful yet, so you didn't have competitors doing the same thing at that time. But what it means is that none of the telecommunication operators wanted to certify the phone for their network, because they were afraid they will be exploits and people will be abusing it, right? Normal phones have elements which are proprietary, which the manufacturers or telecommunication companies don't tell anybody what they do to prevent them to be abused. So it's a little bit like a security by obscurity in a sense, right? So this phone was actually, you couldn't make calls with this phone. It was a phone, but it was never certified to be able to take a SIM card and to connect to anything. In theory, you could make calls, but in practice, none of the operators was actually allowing you to do that. So, you know, calling it a phone was a little bit of a stretch, because you could use it as a smartphone, but you couldn't make calls with it. All right, so say it again. Kind of like a tablet, yeah. So, but then, you know, iPhone and Neo were not the first smartphones, you know, anyway, because if you move to the next slide, that's where the term smartphone was coined. So the term smartphone was coined in '92. It was the first time used, and the smartphone looked like depicted on the picture, right? So what was smart about it? Well, what was smart was you could use it as a phone or as a fax. You could use email. It had a touch screen. It had PDA-like facilities, so some simple apps could run on it, like calendar. And yeah, you can kind of see it fits sort of the definition. So yeah, I don't want to cover the history too much. You can, if those of you who are really interested in the different historical traits of how the developments happened, can browse the slides and check the record from the last year talk. What I want to talk a little bit about is voice versus data, right? So the next slide says voice versus data. how the landscape changed compared to the business models. So when you were the telco operator, you had a bulk of users using quite limited bandwidth of your core network, right? You could have thousand users in Jovic, and you could easily scale it up to 5,000 on some fiber optic cable that you had, right? And they wouldn't, like, by talking with each other, they wouldn't saturate your capacity, right? Now, a single person downloading massive amount of video in a 4K or 5K resolution sucks up enormous amount of bandwidth, right? And then if you have like 1,000 people turning it on, suddenly the requirement for bandwidth goes through the roof. And then if they turn it off, you have like a network which is not utilized at all, right? So dealing with the spikes is much harder, and it can happen at any time. In the past, and currently as well, like voice calls are very hot, for example, in New Year's Eve, like everybody's calling everybody to say Happy New Year, right? So you have this sudden bulk where everybody suddenly has this urge to call somebody. Or if you have some event like on the stadium, you have a soccer game or something, there is a lot of demand for the infrastructure to deal with calls. But in general, people kind of call in a relatively predictable fashion, and the voice is sort of easier. The data is much harder to deal with. So we have these discussions about net neutrality. So from one hand, operators have to deal with the traffic and have to deal with the spikes and with the capacity and with the quality of service, right? So for example, if you are streaming, your YouTube video and one packet drops out, the operator says, I will not send you this packet. Nothing really bad happens. You will probably not notice that, right? But if you're downloading, Xcode for Mac and it's 10 gig download, and one packet operator says, I'm gonna drop that packet, never send it to you, then your entire download is like, it will not pass the checksum, right? You will miss something, and then you will have to do the whole thing again from scratch. So some quality of service depends on what you're actually doing, right? So for some streaming services, you can drop the quality a little bit, and then for some things that are actually connection oriented, like sending file, you have to send everything and in order, right? So there is this constant discussion of net neutrality. And why do we have this discussion? So you all understand that doing a little bit of quality control and quality assurance for traffic is good for everybody. It's good for the operators because they can manage their capacity in an appropriate way, and it's good for customers because I want my files to be delivered like fully, and I want my videos to be delivered as best as possible. But if there is a frame drop, okay, I can deal with it, right? So why do we have so much discussion about net neutrality? Yeah.
One of the reasons is that if you do not have net neutrality, then the network providers can just stand for competition. If they, for example, have a specific service, they can just slow down every other service, or they can speed up some services if they pay them. But in reality, what happens then is they slow everything else down and then just speed up those specific services, and that can also stifle competition just globally and in general.
Yeah. Yeah, very good.
I'm just going to be like a little bit of devil's advocate because net neutrality is often, you only have the posted, but wasn't the main idea that you were supposed to charge more about the amount of data you're actually using? So if someone is using, low amount of data, they could have like a cheaper.
Yeah, so but that's a little bit different, right? So that is about the usage, like how much data do you use, and in a lot of countries you have that. You pay per data cap. Like in New Zealand, we never had an open, uncapped plans. You have to pay for how much you use, right? Yeah, but that is not about neutrality. Like the operators still don't care what sort of data are you using. Net neutrality is they would say, if you're using this, you pay us more. If you're using this, you pay us less. They decide, not you, like how much certain types of data cost. Net neutrality means data is just data. You're paying per byte. They don't care what do you use, right? So what? Yeah. So one is the competition. Yeah.
Another one is censorship.
Exactly.
A company could just be told by the government, or they could have personal interest in stopping certain things from being known, and then they could just stifle any news source that are negative towards them or the party they are part of.
Yeah. Yeah, that's exactly. Those are the two main problems, right? So having kind of an open, unmonopolistic competition, and second one is the risk of censorship, right? You can block some websites, you can block some content, you can only feed some news that are favoring the current government and not the opposition or what not, right? Yeah.
But there's perhaps a secondary aspect is you can't opt out of privacy based on privacy concerns, right?
Yeah.
So if even, okay, we know that providers actually monitor your traffic to some extent, right? But in this case, they are legitimately monitoring your traffic, right? Because they need to know what you are actually requesting in order to route you fast or slow.
Yeah.
So it's a kind of secondary element there as well. So basically you lose privacy by definition. So
yeah. So then the last point is about operating system neutrality, right? So if we agree more or less, then having kind of a leveled playing field for data access and data transfers is a good thing. How it is about operating systems and application neutrality? Is it also a desirable property that if you are an app developer, you're not being controlled by the operating system owners of what you can and cannot run, right? Within bounds, right? Within the bounds of legal system of a particular jurisdictions, and taking away what you might do maliciously, right? So if we say for all normal legitimate apps, should it be your right to have an app delivered to the customers, or should the operating system owners not have OS neutrality and they control what is and what is not possible, right? And here we have the two paradigms. From one hand, we have Google, which decided to go with the more open approach and then allow anybody to submit anything on the platform, and even allow alternative stores to store applications and deliver them, right? And you can enable on your phone install from unknown sources, and you can install from anywhere. And you have Apple, which dictates exactly what is possible and what is not possible, and how does it work, and through which channels the app can and cannot be installed. So they kind of fundamentally differ, and you can have a particular opinion on that, right? I don't care what sort of opinions you have. I just want you to know that there are those two perspectives.